Okay, I figured it's a good place to add this podcast in the context of critical materials for transition to net zero and so on. So this is a paper that argues that the materials needed for electricity generation to meet the global warming targets like 1.5 degrees C and 2 degrees C by 2100 with 67% probability are sufficient in terms of geological resources, and that the emissions from harvesting for these materials is not prohibitively high in terms of staying on target for these global warming targets. So I'm just going to quickly go through this very brief. It's basically a study that again uses integrated assessment models, multiple scenarios, multiple models to come up with future projections for material demands, as we will see. What is the context and scale? Global decarbonization of the electricity generation sector over the next 3 decades will necessitate the construction of substantial new infrastructure such as wind and solar farms, hydroelectric generating stations, and nuclear power plants. Such infrastructure contains substantial quantities of materials from bulk commodities like steel and cement to specialty metals like silver and rare earth metals like tellurium, neodymium, yttrium, and so on. Our estimates of future power sector generation material requirements across a wide range of climate energy scenarios highlight the need for greatly expanded production of certain commodities. However, we find that geological reserves should suffice to meet anticipated needs, and we also project climate impacts associated with the extraction and processing of these commodities to be marginal. So it's not a concern according to this optimistic study. Due to varying material intensity of different power generation technologies, technological choices strongly influence the spectrum of future material requirements. That's okay. So summarizing some points, geologic reserves of materials are sufficient to meet all projected future demands. Wow, that's very optimistic. Magnitude of material needs scales directly with wind and solar deployment. So how much material will be needed depends on how much we rely on wind and solar. Emissions impact of material production are non-negligible but limited in magnitude. That's really good news. So another brief note here. How many tons of steel, copper, silver, and rare earth metals and other materials are needed to build power generation facilities over the next 30 years? This study estimated future global material needs for electricity producing infrastructure across a wide range of scenarios. While wind and solar energy require materials in high quantities, we find these technologies will not be limited by the availability of key metals and materials. So that is not a limitation. However, increasing material demand may require more material production to meet estimated needs. So this is a nice addition to what we discussed before. So let's look at one key figure which is showing us probability distributions of materials used for power sector generation infrastructure in global mitigation scenarios. We will see probability density functions showing the probability distributions, cumulative 2020-2050 materials associated with associated CO2 equivalent emissions, cumulative 2020-2050 power generation, steel and cement requirements, and cumulative 2020-2050 power generation neodymium, silver, tellurium requirements for a selection of 75 integrated assessment models, which we have discussed elsewhere. If you don't know what they are, you can go refer to my podcast on this topic. Categorized end of century category of global mean warming outcome, share of combined wind and solar capacity as a percentage of total energy generation capacity in 2050, and by modeling group. Okay, so lots of information, but the figure is fairly self-explanatory. Materials for future power generation in terms of structural material, cumulative 2020-2050 probability densities, and critical materials cumulative probability density 2020-2050. So this is by warming levels of 2100. Okay, so we are looking at did I miss something? Okay, just the summary here. This is for 2 degrees C, greater than 2 degrees C in red. So tons of demand by power sector will be lower because you are not transitioning to these renewable energies as much as you would under the 2 degrees C warming scenario or the 1.5 degrees C warming scenarios. And you'll have to read the paper to see why you get this double peak over here in the cement requirement. And for steel, you have multiple peaks here, which you have to go and look up for both the 2 degrees C and 1.5 degrees C scenarios in terms of gigatons demanded by power sector. So again, you see that the material needed in terms of gigatons is lower if you let the warming go on and let it exceed the 2 degrees C threshold. Similarly, you can look at it by share of wind and solar capacity in 2050. As we said, deploying more wind and solar capacity will require more material in terms of probability density, again in gigatons demanded by power. So we are looking here at less than 40% or greater than 40%. So greater than 40% will shift the need in terms of probability density of material needed in gigatons towards a higher amount. Of course, there are tails because of the distribution in the probability density function itself. So that's cement and that's steel. And you can see that this steel in the greater than 40% deployment will be much higher in range, but the probability density peak is lower here. These are kind of schematics, but take them as they are because future projections are always uncertain, as we have talked about. But it's good to keep in mind the main message that warming targets can be met without facing material limitations for deploying renewables to stay on target for these warming targets. Critical materials, neodymium, silver and tellurium, and again in terms of percentage of solar and wind. So without going into details, driven by climate targets and solar wind build out, small relative to general societal material demand. So the material needs and the emissions are small relative to general societal material demand. Of course, they are driven by climate targets, but also by solar and wind build out. They dominate the material demand and may require growth in primary material production, which means recycling will be an important part, but you may have to produce more from source materials like cement and steel, and mining for neodymium, silver and tellurium. Cumulative embedded emissions for 1.5 degree scenario and 2 degree scenario in terms of emissions gigaton CO2 equivalent going from 2020 to 2050. Obviously, the emissions will be lower for 1.5 degrees C. There are a number of simulations done with the IAMs shown here, which is a detail, but it's important. And you can see that the percentile ranges for 1.5 degrees C is larger, but the median is here. For cumulative embodied emissions for 2 degree scenario is median is lower, but the range is also smaller. What happens here? Basically, the time series of cumulative power generation material associated CO2 emissions will be higher if you are stricter about the goal of 1.5 degrees C. Will require much more electricity generation with these solar, wind and other renewables like nuclear and hydro, which will require more materials and hence more emissions, whereas allowing for greater warming will manage with lower emissions and lower production and so on. In summary, achieving global climate goals will require prodigious increases in low carbon electricity generation, raising concerns about the scale of materials needed and associated environmental impacts. here. We estimate power generation infrastructure demand for materials and related carbon dioxide equivalent emissions from 2020 to 2050 across 75 different climate energy scenarios, and explore the impact of climate and technology choices upon material demand and carbon emitted. So we have talked about how quick implementation of these transitions will actually reduce the embedded emissions, and here we are focusing on the material needed and the emissions from generating or producing these materials. Material demands increase but cumulatively do not exceed geological reserves. So this is good news. However, annual production of neodymium, dysprosium, tellurium, fiberglass, and solar grade polysilicon may need to grow considerably. Cumulative CO2 emissions related to materials for electricity infrastructure may be substantial, so 4 to 29 gigaton CO2 equivalent in 1.5 degree scenario, but consume only a minor share of global carbon budgets of in the range of 1% to 9% of a 320 gigaton CO2 equivalent for 1.5 degrees C, 66% avoidance budget. So here two things. One is when we do CO2 equivalent, we are converting non-CO2 greenhouse gases like methane, N2O, and so on to CO2 using the global warming potential. And when we talk about the remaining carbon budget, we are relying on the fact that warming is linearly dependent on cumulative carbon. So based on the target, we can calculate or estimate what the remaining carbon cumulative carbon budget is, which is what this 320 gigaton CO2 is for 1.5 degrees C. Our results highlight how technology choices and mitigation scenarios influence the large quantities of materials mobilized during a future power sector decarbonization. So overall, a nice positive message. Of course, there are details in terms of how ore quality and transition of steel and cement to decarbonization will proceed, which are all kind of assumptions you have to make when you go to future projections, and you are relying on technological promises to achieve those goals, so you have to always be careful about whether they will be met and how the geopolitical perturbations of wars and pandemics will affect these transitions as well. Of course, there is the concentration of resources and processing and supply chains and so on and so forth, which are always subject to perturbations and uncertainties as well. Okay, so let's leave it here.